You lie still, perhaps in your bed, perhaps simply in your thoughts, and you imagine the ground beneath you. It feels solid, dependable. A floor that never wavers. Pavement, soil, rock, all firm enough to build cities upon. You trust it without thinking. You step forward every day without wondering what carries you. But now, gently, you let your mind drift downward. Below the grass and concrete, below the roots and pipes and stones, the earth is not as still as it seems. It is layered, like a slow-breathing body. Crust rests upon mantle. Mantle flows above core. And though the word rock suggests something rigid and unmoving, much of our planet's interior behaves more like warm wax than brittle stone. You picture a candle left near a window in summer. It does not melt into liquid, yet it softens. It bends. Given enough time, it flows. The mantle beneath you moves like that, not in seconds or minutes, but in years and centuries. Heat from the planet's deep interior rises slowly, the way warmth travels upward through your hands when you hold a mug of tea. The Earth is not cold inside. It remembers its fiery birth 4.5 billion years ago, when gravity pulled dust together so tightly that stone became molten. That ancient heat still lingers. And in certain places, that heat gathers. Far beneath some regions of the crust, pockets of molten rock form. We call it magma rock, so hot it glows when exposed, yet hidden in darkness below kilometers of solid ground. It is not a raging ocean sloshing wildly. It is more patient than that. It accumulates. It warms. It presses gently upward. You breathe in slowly. Imagine that beneath your feet is not emptiness, but a reservoir, a deep chamber where molten rock rests under pressure. It does not roar. It does not pound. It waits. This is how a supervolcano begins. Not with fire, not with ash, but with warmth and time. The crust above these magma reservoirs acts like a lid on a pot. If you have ever watched water heat on a stove, you know it does not boil instantly. First, tiny bubbles form at the bottom. They cling. They rise slowly. The lid trembles only when pressure builds enough to demand release. Deep underground, gases dissolved in magma behave in a similar way. As molten rock gathers, gases like water vapor and carbon dioxide remain trapped inside. Under enormous pressure, they stay dissolved, quiet and invisible. But if the pressure changes, if the magma rises, or if new heat enters the chamber, those gases begin to separate, forming bubbles. Pressure builds not like an explosion, but like a long inhale held too long. You might imagine a supervolcano as a towering mountain with lava pouring from its peak. But many supervolcanoes do not appear dramatic at all. They often form broad depressions in the land called calderas, vast basins created when the ground collapses after enormous eruptions in the distant past. Forests grow inside them. Rivers cross them. Wildlife wanders peacefully above sleeping heat. From the surface, life feels ordinary. That is part of what makes the idea so humbling. The extraordinary often hides beneath the familiar. The crust under your feet is thin compared to the rest of the planet, like the skin of an apple compared to its flesh. On continents, it may be 30 to 50 kilometers thick. Beneath oceans, thinner still. Below that lies the mantle, extending nearly 3,000 kilometers downward. The scale is almost impossible to hold in your mind, so you do not force yourself to measure it. Instead, you feel it as depth, as layered quiet. Supervolcanoes form in places where unusual amounts of heat rise from below. Sometimes this heat comes from mantle plumes, columns of hotter rock ascending slowly from deep within the earth. They rise like wax in a lava lamp, except their journey takes millions of years. Where that heat meets the crust, melting can intensify. Magma chambers grow larger over time. Not in days. Not in centuries. In spans so vast that human history would fit into a blink. And still, nothing may happen for hundreds of thousands of years. You rest with that thought. The word super might sound dramatic, but it simply describes scale. A supereruption releases more than 1,000 cubic kilometers of material, ash, rock, gas. It is an amount difficult to picture, so you imagine something gentler. Imagine filling 1,000 cubic boxes, each 1 kilometer wide, long, and tall. That is the threshold. It is vast beyond ordinary experience. Yet even such immensity begins quietly, molecule by molecule, crystal by crystal, as magma cools and reheats, melts and reforms deep underground. Crystals grow within magma like frost forming on a winter window. They change its thickness. They alter how it flows. Over time, the chamber becomes a complex mixture of liquid rock, solid crystals, and trapped gas, a dynamic system balancing pressure and strength. The rock above it is strong. Stronger than steel in some ways. But rock is not immune to time and temperature. Heated enough, pressed long enough, it bends microscopically. It fractures in small, almost imperceptible ways. And still, most of the time, balance holds. You realize something gentle here. A supervolcano is not actively trying to erupt. It is not a creature with intention. It is a system seeking equilibrium. Heat rises. Pressure builds. Rock resists. Over immense spans of time, these forces negotiate. Tonight, you simply listen to that negotiation. The earth beneath you feels less like a rigid platform and more like a layered, living presence, not alive in the biological sense, but alive with movement, energy, and memory. The continents drift a few centimeters each year. Mountains rise and erode. Magma cools into stone. Stone sinks and melts again. Nothing is static. Everything is slow. You imagine placing your ear against the ground, not to hear a roar, but to sense a faint hum, the deep circulation of a planet still warm at heart. The supervolcano was part of that circulation, like a pulse that beats only once every 100,000 years. For now, it sleeps. But sleep does not mean emptiness. It means potential. It means stored warmth. It means time stretching quietly ahead. As you drift deeper into stillness, you begin to wonder if such immense power can lie hidden so peacefully. What truly makes a volcano super? What separates an ordinary mountain of fire from something capable of reshaping continents and cooling the entire planet? You hold the word super in your mind. It sounds dramatic, almost cinematic. It suggests capes and thunder and something larger than life. But in geology, the word is quieter than that. It does not shout. It measures. To understand what makes a volcano super, you begin not with fear, but with comparison. Imagine placing a teacup on a table. You fill it with water. That is one eruption, small, visible, contained. Many volcanoes around the world erupt like that. They send lava flowing down their slopes, release ash into the sky, and then settle again. These eruptions can be powerful and dangerous locally, but they are limited in scale. Now imagine filling a bathtub. Then a swimming pool. Then a lake. And then, gently, imagine trying to fill something the size of a small sea. The difference between an ordinary volcanic eruption and a supereruption is not just a little more lava. It is an entirely different category of magnitude. Scientists measure eruptions using something called the Volcanic Explosivity Index, or VEI. It is a scale from 0 to 8, each step representing roughly 10 times more erupted material than the last. Most eruptions that make headlines fall between VEI 2 and 5. A supereruption is VEI 8. It releases more than 1,000 cubic kilometers of volcanic material, ash, pumice, fragmented rock. If you imagine 1 cubic kilometer as a box 1 kilometer wide, 1 kilometer long, and 1 kilometer tall, you would need 1,000 of those enormous boxes to contain the output. The number is almost too large to grasp, so you let it soften into feeling rather than calculation. It is not just the lava that defines a supereruption. In fact, lava flows are often not the main event. Instead, supereruptions are driven by explosive pressure, gas-rich magma that shatters into fine ash and blasts upward with extraordinary force. You picture shaking a bottle of sparkling water. If you open it gently, nothing dramatic happens. But if you shake it first, pressure builds inside. Gas forms bubbles. The moment the cap is loosened, those bubbles expand violently, pushing liquid outward. Magma behaves in a similar way. Deep underground, dissolved gases remain trapped under immense pressure. As magma rises closer to the surface, pressure decreases. The gases expand rapidly, fragmenting the molten rock into ash. The expansion becomes explosive, propelling material high into the atmosphere. In a supereruption, this expansion is not a brief burst. It can continue for days, even weeks. Ash columns rise tens of kilometers into the sky, piercing the stratosphere. The eruption does not merely affect the landscape around it, it touches the atmosphere itself. But what makes such a vast eruption possible? The answer lies in accumulation. Ordinary volcanoes often have relatively small magma chambers that fill and empty more frequently. Supervolcano systems, by contrast, develop enormous reservoirs over immense spans of time. Heat continues feeding these chambers. Magma accumulates in layers. Crystals form and melt again. The chamber grows not as a hollow cave filled with liquid, but as a complex blend of molten rock and semi-solid crystal mush. You imagine it like a thick stew slowly simmering in a pot. Over time, more ingredients are added. The mixture becomes denser, richer, more pressurized. But the lid remains sealed. Eventually, if enough magma gathers and enough gas saturates the mixture, the crust above can no longer contain the internal force. When the eruption occurs, it can empty a large portion of the chamber at once. The ground above collapses into the void left behind, forming a vast depression known as a caldera. This is another quiet detail: many supervolcanoes do not look like mountains at all. After a supereruption, the structure often collapses inward, leaving a wide basin rather than a towering peak. Forests grow inside. Lakes form. From above, it may appear peaceful and unremarkable. Scale hides itself. The climatic effects of a supereruption extend far beyond the eruption site. Fine ash and sulfur-rich gases injected into the stratosphere can reflect sunlight back into space. Global temperatures may cool for years. It is not fire that reshapes the world, but shadow. You imagine sunlight dimming slightly across continents. Crops growing more slowly. Winters lingering longer. The planet responding not with chaos, but with subtle shifts. Yet here is something deeply calming: supereruptions are extraordinarily rare. They occur perhaps once every 100,000 years or more. Human civilization, as you know it, has existed for only a small fraction of that time. The probability within any given lifetime remains very low. And still, the potential exists. What makes a volcano super is not anger. It is scale plus time. It is the combination of vast magma reservoirs, immense gas pressure, and a crust that holds for ages before yielding. It is patience magnified. You begin to sense that super is less about violence and more about accumulation. The Earth does not rush. It layers heat upon heat, crystal upon crystal, century upon century. In this way, a supervolcano is not fundamentally different from other volcanoes. It follows the same physical laws. Magma rises because it is less dense than surrounding rock. Gases expand as pressure drops. Rock fractures when stressed beyond its strength. The processes are familiar, only their magnitude changes. It is like comparing a single heartbeat to the slow pulse of an ocean tide. Both are rhythms. One is simply vast beyond everyday experience. And so you rest with this understanding: a supervolcano is defined not by drama, but by proportion. By the amount of material. By the height of ash columns. By the reach of atmospheric change. You imagine standing on quiet land that once released enough ash to blanket continents. You would not know it by sight alone. The grass would still sway. The sky would still glow at sunset. The enormity would be hidden in layers of rock beneath your feet. How does something so immense remain concealed for so long? The answer lies deeper still, not at the surface where ash meets air, but in the hidden chambers where molten rock gathers slowly in darkness, breathing in and out over centuries, preparing without hurry for a future that may be unimaginably distant. You let your thoughts sink again, gently, below the surface. Past soil and stone. Past roots and groundwater. Past the quiet layers of crust that feel so permanent beneath your steps. You descend not quickly, but slowly, as if floating through warm, dark water. Somewhere far below, there are chambers. Not hollow caves like those carved by rivers. Not empty rooms waiting to be filled. Magma chambers are more subtle than that. They are regions of rock so heated that parts of them melt, forming vast reservoirs of molten material threaded between crystals and solid fragments. You imagine a sponge soaked in glowing syrup. Solid and liquid intertwined. Heat everywhere. For a long time, scientists pictured magma chambers as underground lakes of liquid rock, sloshing and waiting. But modern research reveals something more intricate. These reservoirs often resemble a thick crystal mush, a mixture where molten rock occupies the spaces between countless mineral crystals. It is dynamic. It shifts. It reorganizes under pressure. You picture snowfall, but not in cold air. Instead, crystals grow within molten rock like slow flakes forming in fire. As magma cools slightly, minerals begin to crystallize. Feldspar. Quartz. Pyroxene. Each mineral forms under specific conditions of temperature and chemistry, like notes emerging in a symphony. When more heat rises from below, those crystals may partially melt again. The chamber is not static. It cycles between solidity and liquidity, between stiffness and softness. You breathe in. Magma chambers do not fill overnight. They grow through repeated injections of molten rock rising from deeper within the mantle. Each new pulse adds heat, material, and gases. Over tens of thousands of years, these injections accumulate. Imagine adding warm water to a basin again and again. The temperature gradually rises. The volume increases. The pressure against the edges grows stronger. Deep underground, the surrounding rock presses inward with immense force. The weight of kilometers of crust bears down from above. Under such pressure, gases remain dissolved within the magma, invisible and contained. Water vapor, carbon dioxide, sulfur dioxide, all dissolve like sugar in tea. But pressure is not constant forever. As magma accumulates, it exerts its own force outward. The chamber expands microscopically, pushing against the rock that encloses it. Rock may seem rigid to you, but under high temperature and sustained stress, it behaves more like very thick putty. It bends slowly. It creeps. You imagine pressing your thumb gently into wax. At first, it resists. Then, gradually, it yields. In a magma chamber, this yielding occurs over centuries. The crust above may rise by mere millimeters per year, a motion so subtle that only precise instruments can detect it. From the surface, nothing appears unusual. Trees grow. Rivers flow. Clouds drift overhead. But below, the chamber breathes. When new magma enters, pressure increases. When small amounts cool and crystallize, pressure may ease slightly. It is like a slow inhale and exhale. A geological respiration. Sometimes the system reaches a delicate threshold. If enough magma accumulates in a state that is sufficiently molten, not too crystalline, not too solid, it can mobilize. The crystal mush becomes more fluid. Gases begin to coalesce into bubbles. You picture bubbles forming in rising bread dough. Tiny pockets expanding within a dense mixture. As bubbles grow, they increase internal pressure. The magma becomes more buoyant. It seeks pathways upward. Fractures may form in the overlying rock. These cracks are not dramatic at first. They are hairline weaknesses responding to stress. Magma exploits them, pushing into new spaces, forming vertical sheets called dikes or horizontal intrusions called sills. Most of the time, these intrusions cool before reaching the surface. They solidify quietly underground, adding strength to the crust rather than breaking it. The system stabilizes again. This is important. A supervolcano's magma chamber may experience countless injections and minor movements without erupting. Eruption is not inevitable. It requires specific conditions, enough eruptible magma, sufficient gas saturation, and a pathway that allows rapid decompression. You let that calm you. The Earth prefers balance. It tolerates immense internal motion without catastrophe most of the time. Still, you imagine a moment when balance shifts. If the chamber becomes sufficiently pressurized and the overlying rock cannot contain it, decompression begins. As pressure drops, dissolved gases expand rapidly. Bubbles grow larger and larger, shattering the surrounding magma into fragments. The mixture becomes a frothing, explosive blend of gas and ash. But before such a moment, before any eruption, there are long ages of quiet preparation. Inside the chamber, temperature gradients form. Hotter zones mingle with cooler ones. Chemical compositions evolve as crystals remove certain elements from the melt. Silica concentration may increase, making the magma more viscous, more resistant to flow. Viscous magma traps gases more effectively, allowing pressure to build higher. You imagine stirring honey versus water. Honey resists movement. If bubbles form within it, they struggle to escape. Pressure accumulates. Silica-rich magma behaves somewhat like that honey, thick, sticky, reluctant to release gas. Many supereruptions involve such high silica, viscous magma because it stores enormous volatile pressure before rupture. And yet, even in this complexity, the process is governed by simple physics: heat transfer, buoyancy, fracture mechanics, gas expansion. No intention. No anger. Only laws of nature unfolding over time. The chamber breathes in darkness, unseen. You realize that what makes it powerful is not just its size, but its longevity. It may take hundreds of thousands of years for a chamber to accumulate enough eruptible material for a supereruption. And even then, conditions must align precisely. Most chambers cool partially before reaching that stage. They crystallize. They lock themselves into stone. The potential fades. You rest with that possibility too, that many sleeping giants simply grow old and solidify without ever roaring. Above, you continue living unaware of these cycles. You walk across continents shaped by ancient eruptions whose magma chambers long ago cooled into granite. The dramatic has already passed into quiet rock. Yet in certain regions, heat continues to rise. Mantle plumes persist. Magma injections continue at depth. The breathing goes on. You imagine placing your hand on the ground, not to feel vibration, but to sense warmth carried upwards slowly through layers of stone. It is subtle. It is steady. It is patient. Deep below, crystals form and melt again like embers glowing beneath ash. Pressure builds and relaxes. Rock bends and strengthens. Something is always moving even when you cannot feel it. And as you drift towards sleep, you begin to wonder where, on the surface of this vast planet, such chambers are being watched most carefully. Where scientists have placed instruments to measure each subtle breath of a hidden giant. Where steam rises from the earth as a reminder that the darkness below is not cold at all. Your thoughts begin to travel toward one such place, a wide landscape of forests and geysers, where a supervolcano rests beneath extraordinary beauty, quietly under watch. You arrive gently in a wide, open landscape. Forests stretch across rolling hills. Rivers carve silver lines through valleys. Bison move slowly through mist at dawn. The air smells of pine and earth and distant rain. This is Yellowstone National Park, a place that feels ancient and calm. And yet, beneath this beauty, something vast and warm resides. You imagine standing near a geyser. Steam rises in soft white plumes, drifting upward into cold morning air. The ground beneath you is warm to the touch. Pools shimmer in shades of blue and green and gold, colored by minerals and heat-loving microbes. The earth here feels alive in a different way, not through motion, but through temperature. All of this surface activity is a sign of what lies below. Deep under Yellowstone rests a large volcanic system, one of the most closely monitored on Earth. It is not a towering cone like Mount Fuji or Mount St. Helens. Instead, it is a caldera, a broad depression formed after immense eruptions long ago caused the ground to collapse inward. If you were looking from high above, you might not immediately recognize it as a volcano at all. The caldera spans roughly 70 kilometers across at its widest. Forests grow across it. Lakes fill parts of it. Roads wind quietly through it. Scale hides in plain sight. About 2.1 million years ago, Yellowstone experienced a supereruption. Another followed about 1.3 million years ago. The most recent major caldera-forming eruption occurred around 640,000 years ago. Each event released enormous volumes of ash and volcanic material, reshaping the landscape dramatically. You do not dwell on violence. Instead, you feel the deep timeline. Hundreds of thousands of years between major events. Human civilization has existed for only a fraction of that span. Beneath Yellowstone today lies a complex magmatic system. Modern imaging techniques, seismic tomography, ground deformation measurements, gas analysis reveal that below the caldera sits a large region of partially molten rock. It is not a vast empty cavern filled with liquid magma. It is, as you have learned, more like a sponge of crystal and melt intertwined. Scientists estimate that only a portion of this region is fully molten at any given time. The rest is crystalline, semi-solid, stable. You breathe slowly. The presence of magma does not mean eruption is imminent. It means heat persists. Yellowstone's surface features geysers, hot springs, fumaroles exist because groundwater seeps downward through cracks in the crust. There, it encounters hot rock heated by underlying magma. The water warms, becomes buoyant, and rises back to the surface. When pressure builds in underground plumbing systems, geysers erupt. When water circulates continuously without explosive release, hot springs form. The park's famous features are expressions of a hydrothermal system driven by deep heat. They are whispers, not warnings. And yet, scientists listen carefully. Across the park, sensitive seismometers record even the smallest earthquakes, tremors too faint for you to feel. Most are tiny, caused by the shifting of rock or the movement of fluids underground. Swarms of small quakes occur occasionally, releasing minor stresses. You imagine them like subtle adjustments in a settling house. In addition to seismic monitoring, researchers use GPS stations to measure the ground's movement with extraordinary precision. The caldera sometimes rises by a few centimeters over years, then subsides again. This motion reflects the filling and cooling of magma or the circulation of hydrothermal fluids. It is the breathing you imagine before inhale and exhale on a geological scale. From space, satellites using radar interferometry detect changes in elevation measured in millimeters. The Earth cannot shift here without someone noticing. Gas emissions are monitored too. Carbon dioxide and sulfur dioxide seep through cracks and vents. Changes in gas chemistry can signal shifts in the magmatic system below. You sit beside these invisible instruments in your imagination. They hum quietly. They gather data patiently. There is no alarm sounding. Only observation. This is what makes Yellowstone different from ancient supervolcanoes that erupted without witnesses. Today, the system is watched continuously by teams of geologists, geophysicists, and chemists. The Yellowstone Volcano Observatory analyzes patterns and publishes updates. Transparency replaces mystery. And what do they report? That Yellowstone is active but stable. Earthquakes occur regularly, but most are small. Ground deformation continues, but within expected ranges. Heat flow remains high, but not increasing in ways that suggest imminent eruption. In fact, the magma reservoir beneath Yellowstone appears to be only partially molten, not a vast chamber of eruptible liquid, but a complex mixture with limited immediate mobility. You let that settle into your thoughts. The sleeping giant is not pacing restlessly. It is breathing, slowly, steadily. You imagine lying on warm earth near a steaming pool. Beneath you, kilometers down, magma cools and reheats in cycles that last centuries. Above you, birds call and wind moves through trees. Life continues. It is humbling to realize that something capable of reshaping continents lies beneath such tranquility. Yet it is also comforting to know that geological processes unfold with warning signs, with measurable precursors, with detectable shifts. Supereruptions do not happen without preparation. They require massive volumes of eruptible magma and significant pressurization. Current scientific understanding suggests that Yellowstone's system does not contain enough fully molten material to produce a supereruption anytime soon. The future remains open, but not immediate. You feel the balance here, awareness without alarm. Yellowstone reminds you that Earth is dynamic, yet patient. That beauty and potential power can coexist without contradiction. That monitoring and knowledge allow you to replace fear with perspective. Steam rises into twilight. The ground hums faintly with warmth. Beneath forests and lakes, magma continues its slow transformation. And as you leave this landscape in your mind, you begin to wonder about those ancient eruptions that shaped it, eruptions so vast they left layers of ash across distant lands. What did the sky look like then? What did the air feel like for early humans living under a dimmed sun? Your thoughts drift backward in time, toward one of the greatest eruptions the planet has ever known. You let time loosen its grip. Not years, not centuries, but tens of thousands of years drift past you like slow-moving clouds. You travel back approximately 74,000 years, long before cities, long before agriculture, long before recorded history. The planet looks familiar: mountains, oceans, forests, yet humanity is different. Small bands of early humans move across landscapes, carrying tools of stone and memory and stories rather than books. And in what is now Indonesia, something vast begins to change. Beneath the region that will one day be known as Lake Toba, a colossal magma system has been building quietly for hundreds of thousands of years. Heat rises from deep within the mantle. Magma accumulates. Crystals form and melt again. Pressure grows with patient determination. You imagine the chamber beneath as immense beyond ordinary comprehension, a reservoir filled with silica-rich, gas-laden magma. Thick, viscous, pressurized. Then, eventually, balance shifts. When the eruption begins, it is not a single explosion but a sequence of colossal blasts. Magma fragments violently as dissolved gases expand. Ash columns surge upward, rising perhaps 40 to 50 kilometers into the sky, piercing the stratosphere. The sound would have been indescribable, a deep, continuous thunder echoing across oceans. But you do not focus on noise. Instead, you watch the sky. Ash spreads outward in enormous plumes, carried by atmospheric winds. Fine particles drift thousands of kilometers away. Geological evidence suggests that ash from this eruption settled across South Asia, the Indian Ocean, and parts of Africa. Imagine gray snow falling where tropical rains once nourished forests. The eruption of Lake Toba is estimated to have ejected roughly 2,800 cubic kilometers of material, nearly 3 times the minimum threshold for a supereruption. It is one of the largest known eruptions in the last 2 million years. You try to picture 2,800 cubic kilometers, but numbers dissolve in your mind. So instead, you imagine layers of ash settling across landscapes, thick enough in some regions to bury entire ecosystems. And then comes the shadow. Sulfur-rich gases injected into the stratosphere react to form sulfate aerosols, tiny reflective particles suspended high above the clouds. These particles scatter sunlight back into space. The planet cools. Some climate models suggest that global temperatures may have dropped several degrees Celsius for years following the eruption. It would not have been a sudden ice age, but a persistent dimming, colder summers, longer winters, altered rainfall patterns. You imagine early humans looking upward. They do not know about aerosols or atmospheric chemistry. They simply see a sky that feels muted. Sunlight weaker. Days perhaps hazier. There has been scientific debate about how severe the climatic effects truly were. Some early hypotheses proposed a volcanic winter so intense that human populations nearly collapsed, leaving a genetic bottleneck in our species. Later research suggests the effects, while significant, may not have been quite so catastrophic. Science evolves, just as the Earth does. What remains clear is this: Lake Toba altered landscapes across continents and left geological fingerprints still visible today. Layers of volcanic ash, called tephra, provide time markers and sediment cores. They allow scientists to reconstruct the story long after the eruption itself faded into silence. You breathe slowly. The eruption ends eventually. Magma empties from the chamber. The ground above collapses inward, forming a vast caldera. Over millennia, rainwater fills the depression. Today, Lake Toba stretches wide and serene, its surface reflecting sky and mountain. Beauty emerges from violence. Volcanic ash, though destructive at first, weathers into fertile soil over time. Minerals released from pulverized rock nourish plants. Landscapes regenerate. You realize something gentle here: supereruptions are not only endings. They are also beginnings. But still, you linger with the human question. If you had lived then, if you were among those early people moving across valleys and coastlines, how would you have experienced it? Perhaps ash fell lightly in your region, just enough to change the taste of air. Perhaps seasons felt colder, harvests scarcer. Perhaps stories arose explaining the dimmed sun and strange skies. Or perhaps in some distant places, life continued with little disruption, the eruption too far away to alter daily survival significantly. The Earth's systems are complex. Effects vary by distance, by wind patterns, by geography. A supereruption is global in reach, but not uniform in impact. You let go of extremes. You avoid imagining total darkness or instant extinction. Instead, you picture gradients, areas heavily buried, others lightly dusted. Regions cooled more strongly, others less. Scientific evidence from sediment cores and ice cores helps reconstruct atmospheric changes. Sulfate layers trapped in ice provide clues about past eruptions. Each layer is like a thin memory preserved in frozen time. In this way, the planet keeps records even when humans do not. You feel small here, but not insignificant. Humanity has endured ice ages, droughts, migrations, and yes, even supereruptions. Our ancestors adapted. They moved. They survived. And yet, Lake Toba reminds you of scale. It reminds you that Earth operates on rhythms far larger than individual lifetimes. That a single eruption can leave traces measurable tens of thousands of years later. The sky brightened again eventually. Aerosols settled. Temperatures stabilized. Vegetation returned. Life continued its quiet persistence. You picture the lake today, calm waters surrounded by green hills. Tourists visit without sensing the immensity beneath their feet. The caldera holds no visible memory of its explosive birth except in its vast shape. Time smooths even the greatest upheavals. And as you drift forward again from ancient Indonesia to the present day, you realize something quietly reassuring: we are not unaware now. We do not wait blindly. We study ash layers. We analyze gases. We measure subtle shifts in ground and gravity. Unlike early humans, we have instruments listening. You begin to wonder how, exactly, scientists detect the faint stirrings of magma deep underground. How they distinguish between harmless breathing and meaningful change. How they press their metaphorical stethoscopes against the Earth's chest and interpret its rhythms. The ancient echoes fade, and your thoughts turn toward the quiet rooms filled with monitors and maps, where researchers listen carefully to a restless planet. You enter a quiet room filled with screens. There is no dramatic music here. No flashing alarms. Only steady lines moving gently across monitors, like heartbeats drawn in ink. Scientists sit calmly, watching patterns unfold in real time. They are listening. But not with their ears alone. Beneath the Earth's surface, rock shifts constantly. Most of the movement is small, tiny fractures adjusting under stress, fluids circulating through cracks, distant tectonic plates sliding past one another at the pace of growing fingernails. You cannot feel these motions. Your body is not sensitive enough. But instruments are. Seismographs are placed across volcanic regions like careful sentinels. Each one contains a delicate mass suspended within a frame. When the ground moves, even slightly, the frame shifts while the mass resists motion due to inertia. That relative movement is recorded as a waveform, a trace of motion through time. You imagine placing a stethoscope against the chest of the earth. Every tremor becomes a whisper. Every cluster of tiny earthquakes becomes a phrase in an ongoing conversation. In volcanic systems, certain patterns matter more than others. Swarms of small earthquakes may indicate magma moving through cracks. A change in depth or frequency can signal that pressure is redistributing underground. But even here, scientists move gently with interpretation. Not every swarm means eruption. Most swarms release minor stress and then fade away. Listening requires patience. Beyond earthquakes, researchers measure the ground itself. Imagine standing in one place for years and noticing that the land beneath your feet has risen by 2 centimeters. You would not perceive it without a ruler. But GPS stations, anchored firmly into bedrock, can measure such changes precisely. These stations communicate with satellites orbiting Earth. By calculating the time it takes for signals to travel between ground and satellite, scientists determine position down to millimeters. If magma accumulates beneath a volcano, it can cause the ground to swell slightly. If magma cools or drains away, the surface may subside. The motion is slow, often reversible. You picture the Earth breathing, inhale, exhale, visible only through careful measurement. There are also satellites that do not rely on GPS alone. Radar interferometry, known as NSAR, sends pulses of radar energy from space toward the surface. By comparing signals taken at different times, scientists detect subtle changes in elevation across wide areas. From hundreds of kilometers above, they can see the Earth's skin rising and falling like a sleeping chest. And then there are gases. Volcanic systems release gases through vents, cracks, and soil. Carbon dioxide seeps invisibly from the ground. Sulfur dioxide escapes in faint plumes. These gases carry information about the magma below. If fresh magma rises, gas composition may change. Ratios of carbon to sulfur may shift. Helium isotopes, rare fingerprints of deep mantle material, can increase. Scientists collect gas samples carefully, sometimes hiking into remote areas with portable analyzers. They measure concentrations and compare them to long-term baselines. Again, the key word is comparison. It is not the presence of gas that matters, but change. You imagine a doctor taking your pulse. A single heartbeat tells little. A pattern over time tells a story. Volcanology works in the same way. Even gravity itself becomes a tool. Slight changes in the distribution of mass underground can alter the local gravitational field. Sensitive gravimeters detect these minute differences. If magma accumulates in a chamber, gravity measurements may increase subtly. The planet's weight shifts ever so slightly. All of these data streams flow into observatories, places where scientists integrate information from seismology, geodesy, geochemistry, and remote sensing. They do not rely on one signal alone. They look for convergence. An increase in earthquakes combined with rapid ground uplift and significant gas changes would attract attention. But rarely do all these indicators align dramatically. Most of the time, volcanic systems fluctuate within expected ranges. You feel the calm of this realization. The Earth is restless, yes. But restlessness does not equal catastrophe. It is simply motion within a living planet. Scientists also use computer models to simulate what happens underground. By applying principles of physics, pressure, temperature, rock mechanics, they test scenarios. What would happen if magma volume increased by a certain amount? How would stress distribute through surrounding rock? At what point would fracture become likely? Models are not predictions. They are explorations of possibility. In this quiet room, there is humility. Researchers know that the Earth is complex. No instrument sees everything. No model captures every variable. But together, these tools provide insight far beyond what was possible even a few decades ago. You imagine ancient humans living near volcanoes without warning systems, relying only on visible signs, smoke, tremors, unusual animal behavior. Today, subtle changes are detected long before dramatic surface expressions occur. Preparedness replaces surprise. And still, scientists speak carefully. They avoid certainty where none exists. They describe probabilities, not guarantees. They publish updates transparently, acknowledging uncertainty as part of understanding. Listening to a restless planet requires both technology and restraint. You rest in that balance. The Earth beneath you continues its slow internal circulation. Magma chambers warm and cool. Rock fractures and seals. Fluids migrate through porous stone. Seismographs record faint lines across digital screens. GPS stations report daily positions. Satellites orbit silently overhead, watching for millimeter shifts. There is no silence, only subtlety. As you drift toward deeper calm, you begin to sense that beneath all these measurements lies something even more fundamental, the quiet accumulation of pressure and the passage of time. Instruments can detect movement, but what truly determines whether a supervolcano erupts is not a single tremor or a single rise in ground level. It is the language of pressure and time, spoken slowly in the darkness below. You return now to the deep places beneath your feet. Not to instruments. Not to observatories. But to the slow physics unfolding in darkness. Pressure is not loud. It does not arrive with a shout or a flash. It gathers quietly, molecule by molecule, crystal by crystal. It is the weight of overlying rock pressing downward. It is the buoyancy of magma pushing upward. It is gas dissolved invisibly in molten stone, waiting for space to expand. You imagine holding your breath. At first, it feels easy. Then, gradually, your chest grows tight. The pressure is not sudden, it increases steadily. The longer you wait, the stronger the urge to release. A magma chamber experiences something similar, but on a scale measured in centuries. Deep underground, the surrounding rock presses inward with enormous force. This confining pressure keeps gases dissolved within magma, like bubbles trapped in a sealed bottle. As long as the system remains stable, there is balance. But magma is buoyant. It is often less dense than the rock around it. Slowly, persistently, it pushes upward, seeking space. The crust resists. Rock may seem rigid in your hand, but at temperatures of hundreds of degrees Celsius, under immense pressure, it behaves differently. Over long timescales, it flows not like water, but like extremely thick honey. It bends before it breaks. You picture a wooden beam under steady weight. At first, it holds firm. Over time, it begins to sag slightly. Microscopic cracks form. Fibers stretch. In the Earth's crust, similar adjustments occur. Stress redistributes. Tiny fractures open and close. Minerals recrystallize under pressure, healing weaknesses in some places while concentrating strain in others. Pressure and strength are in constant conversation. Heat plays its part too. When magma accumulates, it transfers warmth into surrounding rock. Warmer rock becomes more ductile, more capable of bending without fracturing. In this way, heat can delay rupture, allowing pressure to build even further. It is a paradox. Warmth both weakens and stabilizes. You let that complexity rest gently in your thoughts. Eruptions, especially supereruptions, are rarely instantaneous decisions by the planet. They are outcomes of long preparation. For a supervolcano to erupt, several conditions must align. There must be enough eruptible magma, not just crystalline mush, but sufficiently molten material capable of flowing. There must be enough dissolved gas to drive explosive expansion. And there must be pathways through the crust that allow rapid decompression. If any one of these elements is missing, the system may settle instead of erupt. You imagine a locked door. Behind it, pressure builds. But unless the hinges weaken or the latch gives way, the door remains closed. Sometimes pressure eases before failure. Magma cools. Crystals grow. Gas escapes slowly through fractures. The conversation ends quietly. Geologists study rock formations left behind by ancient eruptions to understand this language. They examine mineral crystals for clues about temperature and pressure histories. Tiny inclusions trapped inside crystals preserve samples of magma from earlier stages, like time capsules sealed within stone. By analyzing these inclusions, scientists reconstruct how long magma resided in chambers before eruption. Some evidence suggests that large volumes of eruptible magma can assemble relatively quickly, perhaps within centuries or even decades before an eruption, after much longer periods of partial crystallization. This idea is both humbling and calming. It means that even systems that appear stable may evolve over time. But it also means that monitoring matters, because changes can be detected. Still, the key ingredient remains time. Supereruptions do not happen every few decades. They are spaced across intervals of hundreds of thousands of years. Between them, systems may experience smaller eruptions or none at all. Time acts like a buffer, stretching events far beyond a human lifespan. You imagine laying a thin thread across a vast field. That thread represents recorded human history, perhaps 10,000 years. The field around it represents geological time. Supereruptions are scattered across the field, separated by distances so great that entire civilizations rise and fall between them. Pressure builds slowly because the Earth moves slowly. Tectonic plates drift a few centimeters per year. Mantle plumes rise over millions of years. Magma chambers assemble incrementally. Even when unrest increases, when earthquakes cluster or ground swells, the process often unfolds over months to years, not seconds. This slowness is protective. It gives space for detection. It allows stress to release in minor ways. It spreads energy across time. And yet, when thresholds are crossed, the release can be swift. You picture a dam holding back water. For years, the structure stands. The reservoir grows fuller. Small leaks appear and are repaired by natural processes. But if pressure exceeds strength at a critical point, failure can propagate rapidly. In volcanic systems, fracture networks can link suddenly, allowing magma to ascend. Decompression triggers gas expansion. Fragmentation accelerates. The quiet conversation becomes a decisive statement. But that statement is the final chapter of a much longer story. You rest in the awareness that pressure and time are inseparable. Without time, pressure cannot accumulate to superscales. Without pressure, time alone changes nothing. The Earth balances these forces continuously. As you breathe slowly, you recognize a pattern. Most of the time, balance holds. Most chambers cool. Most stress redistributes harmlessly. Most pressure finds small pathways to ease. Catastrophe is rare because stability is common. Still, a question lingers gently at the edge of your thoughts. Given this slow language of pressure and time, given the rarity of supereruptions, could one occur within your lifetime? Could the patient accumulation underway in certain parts of the world reach its threshold soon? The thought does not rush you. It does not alarm you. It simply waits there, quiet and curious, like a distant horizon barely visible in twilight. You sit quietly and let your mind return to the scale of time you have been exploring. Hundreds of thousands of years. Centuries of pressure. Decades of subtle shifts. And now, you wonder, could a supervolcano awaken in your lifetime? You take a deep breath. This is not a question meant to startle you. It is a question meant to place your awareness gently alongside geological patience. Supervolcanoes operate on a rhythm far slower than your heartbeat, far slower than the span of a single life. Consider Yellowstone, for example. The last supereruption there occurred roughly 640,000 years ago. That is a number almost impossible to visualize, a length of time that dwarfs the entirety of human civilization. The probability of a comparable eruption occurring in any given century is minuscule. The Earth is patient, and so must you be in considering its possibilities. Probability replaces fear with perspective. You imagine rolling a die with thousands of sides. One particular outcome is necessary to produce a supereruption in a given year. The odds are low. And yet, low does not mean impossible. It only means distant, stretching across the long tapestry of geological time. You allow the mind to wander to other supervolcanoes around the world, Toba, Taupo, Era. Each has its own deep rhythm, its own pulse beneath the crust. Their histories are marked by rare, immense events spaced by millennia. Human life has crossed paths with their cycles only briefly, a flicker against the span of eons. You breathe in slowly. Even if one did awaken, the signs would appear gradually. Earthquakes too small for you to feel would cluster. Ground would rise millimeter by millimeter, detected by instruments. Gas emissions would change subtly. Scientists would observe and interpret the signals, giving humanity days, weeks, or even months to prepare. Preparation transforms fear into action. You imagine sitting beside researchers, as you did in the previous chapter, watching them analyze seismic swarms, measure uplift, and monitor gas chemistry. Instruments would hum and blink, quietly, systematically. Data would accumulate, patterns would emerge, and alerts would be communicated calmly to authorities and communities. The supervolcano is not a secret monster. It is a patient, measurable system. Its signals are legible to those who know how to read them. And yet, the mind wonders naturally. Could one wake in your lifetime? Could something so immense stir beneath the land you walk on, unseen yet powerful? You reflect on the scale of accumulation required. Hundreds of thousands of years of magma injection. Centuries of gas saturation. Layers of crystal and melt. A chamber must be nearly full, gases must be pressurized, and the crust must reach its breaking point. These conditions are rare. And they are not present everywhere. Most magma chambers never reach eruption stage, they cool and solidify quietly underground. You picture them like deep reservoirs of liquid honey, thick and slow, held beneath waxed layers. Sometimes they settle without ever spilling. Sometimes they are tapped only slightly, their pressure relieved in minor eruptions or earthquakes. You let calm wash over you. The rarity of supereruptions allows perspective. It is unlikely that the Earth's most studied systems, Yellowstone, Toba, Taupo, will erupt imminently. But even the faint possibility invites curiosity. Not alarm. Not panic. Just a gentle awareness of forces larger than your immediate perception. Time becomes your companion in this thought. You sense the long span of geological patience. You recognize that Earth moves with a rhythm that is vast and slow, measured in hundreds of thousands of years rather than decades. Tectonic plates drift centimeters per year. Magma pulses rise slowly. Crystals grow and melt over centuries. Even a supereruption, when it occurs, is the culmination of processes unfolding across epochs. Probability, then, is experienced as a landscape rather than a number. It stretches like distant hills beyond the horizon. The horizon is there, tangible yet unreachable. You do not need to run toward it. You do not need to fear it. You simply acknowledge it as part of the planet's story, vast and deliberate. You let yourself imagine the scale in another way. Picture a forest that grows for thousands of years. Trees rise slowly, layer upon layer, until the forest forms a dense canopy. You think about your own life in this context. Daily concerns seem smaller. Even urgent worries fade when placed beside the slow, deliberate unfolding of Earth's inner rhythms. You feel a sense of connection to something larger, something older than human history, yet intimately intertwined with it. You remember that probability is a companion to patience. Low likelihood does not erase respect. Distant possibility does not demand fear. Instead, it invites attentiveness, wonder, and careful observation. It invites you to marvel at the intricate, slow dance of pressure, heat, and time beneath the ground. You picture standing in Yellowstone today. Steam rises gently from geysers. Rivers wind through valleys. Trees sway in a light wind. Beneath your feet, magma pulses slowly, pressure builds and eases, crystals form and melt, and the earth breathes in silence. This is the ongoing story of a restless, living planet, vast, measured, and patient. And as you settle into this reflection, your thoughts drift naturally to the next consideration. If a supervolcano were to stir, how would the sky itself respond? How would light, air, and weather bear witness to its awakening? The answer is not immediate. You lift your thoughts upward from the earth to the sky above. It stretches endlessly, pale and delicate, yet full of hidden power. You begin to imagine it changing, not with sudden storms, but in subtle, almost imperceptible ways. What if a supervolcano released enough ash to cloak the sun, even slightly? What stories would the atmosphere tell then? Ash does not fall as a single sheet. It drifts in plumes, carried by winds high into the stratosphere, tens of kilometers above the Earth's surface. Here, the particles are not just dust, they are tiny mirrors, scattering sunlight back into space. The sky itself softens, muted by the presence of these particles. Sunlight becomes less direct, less warm. A gentle veil descends across continents. You feel this change as a cooling, not a panic. Temperatures drop slowly. Days that once carried warmth now carry a slight chill. Summer warmth is muted, winter cold may extend. The atmosphere itself becomes part of the story, interacting with wind patterns, cloud formation, and precipitation. Imagine a world where subtle shifts ripple across the planet. Crops feel the difference first. Plants are sensitive to both temperature and sunlight. Even a drop of a few degrees Celsius can slow growth, alter flowering, or reduce yield. Grasses, grains, and forests all respond in kind. You picture the fields bending differently in the wind, leaves turning slightly earlier in autumn, rivers running a touch slower due to changing snowmelt. And yet, change is gradual, not instant. It is not the dramatic imagery of movies or nightmares. The Earth rarely acts in cinematic leaps. Instead, the cooling spreads slowly, a global sigh in response to the injected particles. You imagine early humans, or even ancient civilizations, watching the sky. The sun looks dimmer. Shadows grow less defined. The horizon softens. They cannot explain sulfur-laden haze in scientific terms, but they can perceive its effect. Crops may fail or yield less. Animals may migrate differently. Seasons feel slightly altered. Life adjusts incrementally, responding to a world where the atmosphere itself has been subtly transformed. Science allows you to understand these processes. Modern models suggest that supervolcanic eruptions can inject hundreds of millions of tons of sulfur dioxide into the stratosphere. Chemical reactions convert this gas into reflective sulfate aerosols, creating a layer high above the weather. This layer persists for years, reflecting sunlight and slowly settling as fine particles. Temperatures on the surface may decline by several degrees globally, enough to shift climate patterns. You let that scientific understanding blend gently with imagination. You see fields, forests, and cities all under a soft, silvered light. The sun is still present, but diffused, as if peering through a translucent veil. Rivers reflect muted glimmers. Snow lingers longer in mountains. Summers feel cooler, winters stretch slightly. Life adapts, not with panic, but with subtle adjustments. Wind currents carry ash around the globe. Monsoons may weaken, jet streams may shift. Rainfall patterns bend. Some regions grow drier, others wetter. The Earth's climate acts as a fluid system, connected in ways both visible and invisible. Every change, every shift, has consequences elsewhere. You can trace it like ripples in a pond, spreading ever outward, connecting distant landscapes in a quiet conversation. And yet, humanity's perspective allows preparation. In a modern context, monitoring ash dispersal, predicting its impact on agriculture, and understanding the atmospheric chemistry can mitigate harm. Aviation, for example, depends on awareness of fine particles. Crops can be monitored. Populations can plan. Scientific knowledge softens the uncertainty, even if the scale of change is vast. You watch ash clouds in your mind drift like slow-moving rivers in the sky. They twist, curl, and spread. Sunlight scatters through them, softening shadows. Mountains fade into muted tones. Oceans shimmer under pale glimmers. The world seems smaller, yet you realize that this pale sky connects everything: continents, weather, ecosystems, and humans in an invisible web of consequence. Temperature change affects not just crops, but humans themselves. Heat waves lessen, winters bite slightly harder. Patterns of disease and migration shift subtly. Rivers swell differently. Food availability fluctuates. Societies adapt, gradually. You imagine that delicate resilience, quietly built, responding to forces far larger than immediate perception. And the sky itself remains alive. Aerosols descend slowly over years, particles settling into dust, soils, and oceans. Rain washes some down. Winds transport others. The pale veil thins. Life continues to adapt. Earth restores balance in its own time. You feel the rhythm of this process. It is slow, deliberate, measurable, yet awe-inspiring. The Earth does not act in haste. Even when the scale of change is global, the unfolding is gentle when seen in the long view. Time allows observation, adaptation, and understanding. And within this vision, you perceive both fragility and strength. Ash can dim the sun, shift weather, and alter ecosystems. Yet life persists. This understanding softens the fear that might have crept into your thoughts. Instead, you are filled with awe for the planet's capacity to change, for its rhythms, and for its patience. You feel a sense of humility, standing beneath an invisible sky that reacts and adapts slowly, measured by processes that operate on a scale far beyond any human lifetime. You imagine yourself watching the sky at dusk. The sun glows faintly through the haze. Colors are softened, pinks, oranges, and purples muted by dust and light scattering. Shadows lengthen slowly. The world seems intimate, yet immense. You sense that everything, from the soil beneath your feet to the clouds overhead, is interconnected. And as you close your eyes gently in your mind, you sense the subtle lesson of pale skies, that change is often quiet, distributed across space and time, and that the earth communicates its rhythms through small, measurable, and persistent shifts. From this perspective, you understand why vigilance matters, why monitoring matters, and why comprehension replaces fear. The sky is not threatening. It is informative. It is a participant in the story of the earth, revealing the consequences of subterranean processes above the ground, over continents, and across decades or centuries. And as the day fades, your mind drifts toward the question of human preparedness. How does a species accustomed to rapid change adapt to slow planetary shifts? How does technology, observation, and foresight help navigate a world where time stretches vast and processes unfold beyond immediate perception? You feel a gentle bridge forming in your thoughts from understanding the pale sky and its subtle consequences, toward a reflection on human capacity for awareness, adaptation, and resilience. This bridge leads softly to the next chapter, where the story of monitoring, communication, and human foresight begins to unfold, without hurry, without alarm, but with profound curiosity. You step back from the pale skies, letting the image settle gently in your mind. Now, your attention turns to yourself, to the world you know, to the humans who live alongside forces far older and far larger than any of us. You imagine communities connected across continents, instruments streaming data, scientists sharing observations instantly. The age of preparedness is upon you. Unlike early humans who could only observe smoke, hear distant rumbles, or see the sun dim through ash, you live in a time of measurement. Satellites orbit quietly overhead, radar pulses scanning the surface. GPS receivers detect ground movements invisible to the naked eye. Seismic networks register tremors that your body could never perceive. Gas analyzers sample invisible emissions in real time. Computers synthesize it all, searching for patterns, teasing out signals from noise. Preparedness replaces helplessness. You picture a network of observatories, scattered across volcanic regions. Each station is a quiet guardian. Seismometers hum. Thermometers measure subtle heat variations. Gas detectors sniff the air for carbon dioxide, sulfur dioxide, and trace gases. Every reading contributes to a mosaic of understanding. Together, these tools form a web of insight, a planetary nervous system, sensing, observing, interpreting. And then there are humans, interpreting the data. Researchers sit patiently, like watchers by a deep river, noting shifts in flow, patterns in the currents, subtle changes in temperature and color. Alerts and warnings are carefully calibrated. Probabilities, not certainties, guide action. A rising ground signal does not become panic, it becomes preparation, assessment, communication. You breathe in slowly, feeling the contrast with the past. There is foresight where there was only uncertainty. Knowledge replaces fear with understanding. Communities can plan evacuations, protect infrastructure, prepare food systems. Technology, communication, and science allow intervention not against the force of the volcano itself, but against the risks to human life. Resilience becomes a quiet strength of civilization. Even with all these tools, you sense humility. Technology does not control geological time. It observes. It informs. It communicates. The earth beneath your feet still moves according to its own rhythms. Magma chambers accumulate, gases pressurize, and crystals form over centuries. Your instruments cannot hurry these processes, they can only read their story. Yet knowledge is transformative. Awareness allows planning. Monitoring allows early response. Global networks mean information flows swiftly across borders. One country's observatory can alert the world to changes in another. Scientists share models, maps, forecasts. Governments can coordinate, societies can prepare. You imagine yourself in a command room, maps spread across a table, screens glowing softly. You see seismic waves ripple across monitors. You watch GPS markers inch upward. You note shifts in gas composition, patterns forming across time and space. Each signal is a word in the ongoing conversation with the planet. Preparedness is the bridge between human vulnerability and planetary scale. Even with this knowledge, you are reminded that Earth's processes are vast and patient. The planet does not hurry to remind humans of its power. Volcanoes operate on timescales measured in centuries and millennia. Supereruptions are not seasonal, they are epochal. Technology can detect, interpret, and warn, but it cannot shorten or accelerate the buildup. Humans must learn patience, too. You feel the balance between power and awareness. Modern societies have developed early warning systems, emergency response plans, and communication networks. Communities can evacuate, food stocks can be mobilized, medical care can be prepared. Critical infrastructure can be monitored and reinforced. The emphasis is on preparation rather than reaction, on observation rather than fear. And yet, even as you appreciate human ingenuity, you are aware of limits. Instruments can fail. Models can misrepresent complexity. Communication networks can falter. Despite your capacity to measure and anticipate, the Earth retains autonomy. Its inner rhythms are not yours to command. Technology boasts a time, to the scale of pressure, heat, and rock, no matter how advanced your sensors or fast your networks. You imagine a world in which humans live with this awareness daily. Children learn that volcanoes exist not as monsters but as patient forces. Communities practice drills, maintain infrastructure, and communicate effectively. Scientists, policymakers, and citizens share understanding, creating layers of resilience that mirror the layers of the earth beneath. The presence of knowledge does not erase respect. It deepens it. You visualize the contrast with earlier ages. People centuries or millennia ago could only respond when ash fell or ground shook. They were vulnerable to surprise, to the immediate consequences of natural forces. Today, observation and preparedness transform the relationship. Risk is not eliminated, but it is measured, understood, and mitigated. And in that understanding, there is calm. You realize that civilization itself is a form of adaptation. Our species has built tools to extend perception, systems to track invisible changes, and protocols to act in advance. Even as the Earth operates at its slow, deliberate pace, humanity moves with intention within the space allowed by knowledge. You feel the quiet strength of this coexistence. Technology does not dominate the Earth, it listens. Humanity does not command eruptions, it observes. Together, you participate in a relationship that is patient, respectful, and informed. You picture steam rising gently from a Yellowstone geyser. You imagine the same ground, decades or centuries earlier, moving imperceptibly beneath the crust. Sensors detect slight shifts, monitor gas escape, and record earthquake swarms. Satellites measure millimeters of ground deformation. All of these observations are stitched together into understanding a narrative constructed from data, interpreted by humans, communicated across time zones and languages. And yet, the Earth reminds you gently of scale. Pressure builds slowly. Magma circulates over centuries. Crystals grow and dissolve. Supervolcanoes do not hurry, and your instruments cannot rush them. Technology enhances perception, but patience remains a necessity. In this balance, you sense reassurance. You are part of a species capable of careful observation, anticipation, and coordinated action. You are aware, prepared, and capable of responding wisely should subtle warning signs emerge. At the same time, you recognize humility as a companion. The forces beneath Yellowstone, Toba, or Taupo operate according to geological time, not human schedules. They remind you that Earth's history is vast, continuous, and patient. Even in an age of technology, there is awe and respect for processes that far exceed individual or collective lifespans. As night falls in your mind's eye, you watch the landscape settle. Trees sway in a gentle wind. Rivers reflect the fading light. Steam rises softly from thermal pools. Satellites orbit quietly overhead. Instruments hum. Scientists review data, discuss observations, and prepare for contingencies. Life continues with vigilance and understanding. And as you rest in this thought, your mind drifts toward the next realization that volcanic activity, though disruptive, is not solely destructive. There is creation in every eruption. Landforms are reshaped. Soils are enriched. Valleys emerge where ash and lava once fell. The earth renews itself even as it challenges life. You close your eyes and imagine the aftermath of a great eruption. Ash blankets valleys. Rivers carry sediment downstream. Lava cools into jagged, black rock. At first, it feels stark, almost barren. The land seems quiet and lifeless, as if the world is holding its breath. But beneath this apparent stillness, transformation quietly begins. Volcanic ash is not mere dust. It carries minerals that were locked in deep rock and magma, transported upward by immense pressure. When it settles onto the surface, it enriches soil, providing nutrients that can sustain life for generations. The earth recycles itself in ways both subtle and profound, teaching patience and resilience to those who watch closely. You walk along a valley coated in soft gray ash in your imagination. Small plants begin to poke through the dust. Moss and lichen cling to rocks, capturing moisture from the air. Tiny insects follow, and seeds carried by wind or birds find fertile ground. Life finds its way, persistent and patient. Even the hardest lava, over centuries, cracks and weathers into soil, ready to support forests and fields. Mountains, once violent and eruptive, begin to shape new landscapes. Lava flows harden into ridges. Pyroclastic deposits form gentle slopes. Valleys may deepen as streams carve new paths. Craters collect water, forming lakes. The land changes, not chaotically, but gradually, sculpted by the forces that first seemed destructive. You realize that destruction and renewal exist in a slow, geological conversation. One cannot happen without the other. The force that obliterates forests also provides the mineral foundation for the next generation of growth. Ash that darkens the sky and chills the air carries the seeds of fertile soil, nourishing life for decades or centuries. Even human civilization benefits from this transformation. Volcanic soils produce abundant crops in regions that might otherwise be infertile. Cities rise near ancient calderas, drawn by the richness of the land and the warmth of geothermal energy. Steam vents and hot springs create opportunities for energy and tourism. Life adapts to and even embraces the lingering presence of a volcano's legacy. You feel a gentle rhythm in this process, a heartbeat of renewal. The earth does not act with malice. It is not fragile, it is resilient. Each eruption, each layer of ash, each flow of lava is part of an intricate cycle of destruction and creation. You watch centuries unfold in slow motion, imagining ecosystems that recover, landscapes that flourish, and life that thrives against the odds. Volcanic islands, such as those in the Pacific, emerge from the sea after submarine eruptions. Over decades, rock cools and weathers. Lichens colonize. Plants arrive on floating debris. Birds bring seeds. The barren rock becomes home to forests, creating habitats for countless species. You sense the patience required. Time, moisture, and resilience collaborate to allow life to flourish where there was once nothing. You also notice rivers. Ash and tephra may initially block waterways, but over time, water carves new channels. Sediment enriches floodplains. You watch in your mind as mountains of cooled lava erode, forming nutrient-rich soil for vegetation. Forests reclaim slopes, roots stabilizing loose material. Wildlife returns. Birds nest in crevices. Insects pollinate new plants. The cycle continues, slow but unbroken. Even in human timescales, you see echoes of this renewal. Farmers plant in ash-laden fields, yielding abundant harvests. Communities harness geothermal energy for warmth and electricity. Scientists study the soils, learning how minerals from ancient eruptions sustain ecosystems. Knowledge becomes part of the renewal, a way for humans to participate in the Earth's rhythm. You notice that volcanic landscapes are dynamic. They do not remain static. Valleys deepen. Lakes form and evaporate. Craters fill with vegetation. Geology is a story written slowly, one layer at a time, sometimes interrupted by bursts of dramatic change. The Earth's narrative is long, patient, and ongoing. And yet, in all this transformation, there is harmony. Life adapts. Humans adapt. Species migrate, seeds disperse, and ecological systems find balance. The planet's surface is neither static nor fragile. It is responsive, creative, and resilient. You reflect on the interplay of time and energy. A supervolcano may seem terrifying in its potential, but in the fullness of centuries, its eruptions contribute to the richness of the Earth. Life follows the contours of volcanic deposits. Rivers and rain shape them. Seeds and animals colonize them. Each eruption lays the foundation for something new. Even the largest calderas, like Yellowstone or Toba, are not merely reminders of past upheavals. They are landscapes in the midst of continuous evolution. Their forests, lakes, and rivers are chapters of renewal, written slowly after dramatic events. The Earth balances violence with life, heat with growth, destruction with creation. You sense that transformation is not only physical but also philosophical. The Earth demonstrates resilience in the face of immense energy. Time allows recovery, adaptation, and flourishing. Patience is embedded in the planet's processes. And by observing and respecting these cycles, humans learn the quiet lesson of endurance. In your mind, you see a mountain range shaped by ancient eruptions. Valleys cradle rivers and meadows. Forests stretch over cooled lava. Wildlife moves through the shadows and light. The land bears the marks of previous upheavals, yet it thrives. Each layer of ash, each ridge of rock, tells a story of transformation, slow and patient. You feel a sense of reverence. The planet is not fragile. It is profoundly transformative. Every eruption, every flow of lava, every plume of ash contributes to a cycle that sustains life in ways both subtle and grand. Destruction carries creation within it. Violence carries renewal. The earth teaches patience, resilience, and trust in slow processes. You watch the scene shift into centuries ahead. Forests grow taller. Rivers carve deeper paths. Communities cultivate fertile soils. Life thrives in ways unimaginable in the immediate aftermath of eruption. You understand that the passage of time softens even the harshest consequences, allowing continuity, growth, and adaptation. And as you close this chapter in your mind, you notice the quiet rhythm beneath it all. Deep underground, magma continues to flow. Heat moves slowly through rock. Pressure builds imperceptibly. The processes that created valleys, lakes, and fertile soils today are also laying the groundwork for the next transformations long into the future. The earth is patient, and in that patience, it teaches you calm. You rest in the awareness that life and land endure, transform, and renew, preparing silently for the chapters yet to unfold. And somewhere beneath the surface, the pulse of heat continues, a reminder that even as the world above flourishes, the quiet rhythm of renewal is ongoing. You lie back in your imagination, letting the earth's gentle pulse guide your thoughts. The land around you seems familiar, quiet, and steady. Rivers meander lazily. Trees sway in soft breezes. The sun dips toward the horizon, painting the sky with muted golds and purples. You breathe slowly, and with each exhale, you sense the steady heartbeat of the planet beneath. It is patient, deliberate, and continuous. Beneath this calm surface, immense energy sleeps. Magma still circulates in vast chambers, warmed by the Earth's core. Heat moves through rock, slowly softening stone. Pressure remains contained, spread across immense spaces of crust and mantle. Though the potential for eruption exists somewhere in the distant future, for now, the giant is resting. You notice the paradox of observation and stillness. Scientists continue their work, monitoring subtle tremors, measuring ground deformation, sampling gases. Instruments hum and record data, quietly attentive. They track, they measure, they analyze. Yet all these observations occur within a system that remains fundamentally patient. The Earth does not hurry to display its power, it moves according to rhythms far slower than human urgency. You reflect on the concept of vigilance without panic. Preparedness does not demand constant worry. It simply requires awareness, understanding, and readiness to respond. Humans, with their networks of sensors and knowledge, coexist with geological forces that operate across millennia. The balance is delicate, but it is managed through observation, insight, and respect for time. Your mind drifts toward the landscapes above these sleeping giants. Yellowstone's forests, rivers, and geysers seem serene, yet beneath lies an intricate and dynamic system. Steam rises through vents. Crystals grow in magma chambers. Tiny shifts ripple through rock. Gas escapes through minor fractures. The processes are continuous, unseen, yet always present. You realize that the Earth's life is not just above ground. It pulses quietly below, like a heartbeat felt rather than heard. You imagine the perspective of those who study these systems. Every tremor, every millimeter of ground uplift, every gas emission is part of a story. Scientists read these signs like chapters in a long and patient narrative. They understand that eruptions are exceedingly rare, and yet, they respect the forces that could, one day, transform landscapes. Their knowledge tempers fear with preparation, vigilance with calm. Even in the quiet, you sense the continuity of cycles. Pressure accumulates. Heat flows. Magma circulates. Minerals crystallize and dissolve. Geological processes do not stop, and yet, they do not demand alarm. The Earth moves according to its own rules, patient and rhythmic, indifferent to human time but responsive to observation. You allow your imagination to wander across centuries, noticing how the land evolves slowly. Valleys deepen, rivers adjust their courses, forests reclaim cooled lava, and soils enrich themselves with minerals from ancient eruptions. Life adapts gracefully to these subtle transformations, finding new ways to thrive in the wake of change. The Earth is resilient. It renews itself continuously, balancing destruction with creation, chaos with order. Now, you consider your own presence in this moment. You feel grounded, supported by the solid earth beneath your feet. The knowledge of hidden heat, circulating magma, and pressure-filled chambers does not create fear. Instead, it cultivates awe, curiosity, and a calm respect for forces beyond your control. Awareness becomes a companion, patience a teacher. You sense the elegance of time at play. Supervolcanoes exist on scales far beyond your own. Human lifespans are mere flickers compared to the patient accumulation of pressure and heat beneath the crust. Eruptions, when they occur, are rare, epical events, not immediate threats. And yet, the very knowledge of these processes allows for coexistence, preparation, and a deeper appreciation of the planet's rhythms. As you lie in this imagined landscape, you notice the soft interplay between stillness and motion. Above ground, life flows in familiar patterns. Animals move through forests. Streams ripple over stones. Trees sway gently. Humans live, work, and create. Below ground, magma moves slowly. Crystals form and dissolve. Heat pulses. Pressure accumulates. Motion exists, yet it is imperceptible to most senses. You recognize the duality of calm above and persistent activity below. In this awareness, you find comfort. The earth is not inert. It is not fragile. It is alive in its own way, patient and transformative. It teaches you that stability and change can coexist. That vigilance does not require anxiety. That slow processes carry both risk and opportunity, destruction and renewal, danger and beauty. You picture the night sky above Yellowstone. Stars twinkle through the cool air. The moon casts silver light across meadows and rivers. The land is quiet, yet not still. You feel the pulse of heat beneath your feet, the slow rhythm of deep chambers, the patient accumulation of pressure that may or may not resolve in eons to come. You rest in the knowledge that for now, everything remains balanced. And in that balance, your mind begins to drift towards sleep. You carry with you the sense of awe at the slow, magnificent forces beneath you. You hold curiosity for the Earth's rhythms, respect for its power, and calm for your own place in its vast timeline. The patient heart of the planet beats steadily, beneath layers of rock, soil, and life, waiting and watching as it has for millennia. As you drift further into the calm of night, your thoughts settle on the gentle lesson this journey imparts, that the earth is both formidable and patient, unpredictable yet continuous, and that your place within it is one of quiet observation and trust. You carry with you the rhythm of deep heat, the knowledge of slow processes, and the peaceful awareness that while the planet's inner heart continues to beat, your own heart can rest safely above it. And somewhere deep below the surface, where time stretches far beyond a single lifetime, the patient rhythm of the supervolcano continues, quiet, constant, and enduring, as if reminding you that even in the vastness of geological time, calm, continuity, and resilience persist, guiding you gently towards sleep.